Meanwhile, to understand why it was a puzzle that the cosmic microwave background had almost exactly the same temperature in every direction, remember the cosmic horizon limit to our vision. We are only able to see those parts of the universe where light has traveled just a bit more than 13.7 billion light years to reach us. That is our cosmic horizon. It is not just a limit to our vision, it is the limit to any sort of information whatsoever. Beyond our cosmic horizon, absolutely no information from anything can have reached us, since nothing is capable of traveling through space at a speed greater than the speed of light. So in the illustration before you, light from point A is just now reaching Earth in one direction, while light from point B is just now reaching Earth in another direction. Earth is at the edge of the cosmic horizon limits for both points A and B, yet there is no way that point A can see point B, or point B can see point A. If there were galaxies at our observable horizon at opposite ends, each would be beyond the other's observable horizon. So there is no way they could have exchanged any kind of information. What we actually see at our observable horizon is not galaxies, but the cosmic microwave background, 2.725 Kelvin. How did it all get to be the same temperature if it could never have exchanged information? If we switch to looking at a space-time diagram, where time running forward goes towards the top of the picture, we can better see both the problem and how inflation resolves the problem. If points A and B were extremely close together in the universe before inflation happened, then they would have been able to exchange particles and information between themselves, perhaps several times over. It would have been as if they were two spots really close together within one mass of ionized plasma, and the temperature equalizes throughout that mass. Then inflation, very suddenly, very dramatically, and almost instantaneously, carries them so far apart that they are vastly beyond each other's cosmic horizons. Eventually, the horizons grow as the universe ages, and at least now we are able to see both light from point A and light from point B, even though still to this day they cannot see each other. But since they had time to equalize their temperatures before inflation, we now see everywhere we look in any direction on the cosmic microwave background the same 2.725 Kelvin temperature. But inflation's greatest triumph is how well it explains the origin of the structures that we see in the universe today. Recall that before inflation, the universe was full of many, many quantum fluctuations. But quantum fluctuations are by their nature extremely small. It seems very unsatisfying to describe something as large as a cluster of galaxies as having an origin in a quantum fluctuation. But inflation actually does it for us. By enlarging the original fluctuations of the universe by something like 10 to the 50th times, one can take an incredibly tiny fluctuation and make it large enough for the purpose. The way inflation is expected to have worked, the larger the universe got, the faster it expanded. Once it had expanded to twice its original size, it would expand twice as quickly. Once 10 times its original size, 10 times as quickly. Quantum fluctuations on small scales would continue through the period of this rapid inflation. So the small fluctuations that got a head start would enlarge to tremendously greater sizes than the fluctuations that arose just an instant later. And as inflation unfolded, we would see fluctuations of every single size developing in the universe. The ones forming later remaining small but growing rapidly, and the fluctuations that formed earlier enlarging to scales even bigger than the observable universe of today once the entire inflation is done. Do we see this kind of scale invariant structure in the universe today? That is, do we see structures of all sizes? You may be thinking no. But let's take a look at the cosmic microwave background very closely. This is an all-sky view of the cosmic microwave background. 360 degrees in all directions mapped onto a projection, similar to a map of the world that shows the Americas and Asia and Africa all in one projection, but it actually is an all-around map. You can see structures in the anisotropies of the cosmic microwave background that appear to extend across half the universe. Those structures seem a lot larger than the largest structures that we say exist in the universe today, and they are. But keep in mind that the little blemishes that you're seeing in this map are just tiny, tiny, tiny little fraction of a percent deviations in density. So the universe is still immensely smooth. Only structures that were small enough that over the 13.8 billion year history of the cosmos, there was enough time for gravity to make them clump up. Those have become larger structures. The even bigger things from the original time, they were such tiny deviations from perfect smoothness that they did not lead to larger structures. And the distribution of different size scales of things we see in the cosmic microwave background, exactly what inflation had predicted. So do all these impressively successful predictions prove that inflation really happened the way we just said it did? Well, no, not yet. We don't have a proof of inflation yet. In fact, the way science works, we never will have what would be considered an absolute proof. We don't have absolute proof of anything. One of these days, rocks might fall up, and then we'll wonder about the law of gravity. But the weight of the evidence so far has been profound and impressive, immensely impressive, considering we're talking about an event that happened within the first 10 to the minus 33 of a second of all existence. It's amazing to stand in front of a classroom and with a straight face say that we think we know what happened only 0.32 zeros in a 1 of a second after creation, and that we have an impressive load of evidence to back it up. That is truly amazing. But there is one more subtle prediction still to be tested. It is very subtle. Inflation is predicted to have sent gravitational waves through the early universe, literal ripples in the fabric of space-time. And these very weak gravitational waves persisting today would have a slight effect on the polarization of the cosmic microwave background. Testing that is still in progress. And there's actually a viable rival theory to inflation, which we've described already as an alternative to explaining dark energy, the colliding brain hypothesis. To review it very briefly, the idea of colliding brains is that our universe is a three-dimensional sheet separated in a fourth dimension by another parallel universe. The Big Bang happened when the two parallel universes collided simultaneously everywhere within them at once. They then separated, and they are now just coming back together. Believe it or not, the colliding brain hypothesis makes exactly the same predictions as cosmic inflation, except for one very tiny detail about the gravitational waves. And right at this moment, there is a microwave probe trying to make the test that will tell the difference. The European Space Agency's Planck probe has currently mapped the cosmic microwave background in the best detail yet, and maybe as soon as next year will release the polarization measurements that will tell the difference between cosmic inflation and the colliding brain hypothesis. Now that is science.